Let me start the recording. Perfect. Awesome. So, welcome everyone to Santa Cruz Artificial Intelligence's first official speaker event of the quarter. We're really lucky and very honored to host Professor Jesse Thomason at USC. And yeah, I think let's kick it off. So, Professor, I know you already did this a bit, but if you want to get a quick lead in into what you're going to be talking about today.
Yeah, sure. I'll do that in a moment. I did notice the screen sharing is disabled generally. Can you enable it for me or co-host me?
Yep, you should have access now.
Great. All right. Can you all see these slides?
Yep.
Awesome. So thank you, Rahul, both for the invitation and the quick introduction. Just to reiterate, I'm Jesse. I'm an assistant professor down in USC, down the coast from y'all, and I work at the intersection of language and robotics historically. And what I'll be focusing on today in this brief lecture is particularly the application of large language models to robotics, since that's really where things have started to pick up in the last couple of years. This should take half an hour to 40 minutes with Q&A at the end. So that means there's time if people want to interrupt during the talk. If you find something particularly engaging and you want to ask about it, or you have a question, please just feel free to unmute and interrupt for that. So I want to start with a quick motivation from the perspective of people who are interested in AI and robotics, why we might want language capabilities on robots in the first place. And I think this example on the right is what we've seen more frequently. So this is work from Google from almost 2 years ago now, called SayCan, which you've probably seen some press releases for. You can look at this top left video where the robot is told, can you move a Coke can to the far counter? So we're seeing an egocentric view of the robot, finding the Coke can, picking it up, moving to another counter and dropping it. If we look at this second video, it's how would you pick up the jalapeno chips and move it to the trash can? And it goes, picks up the chips, drives to the trash can, sort of, and drops it off. Actually drops it in the middle of the ground near a trash can, but you get the idea. So this sort of like language-guided robot behavior is typically the first thing that comes to mind when people think about language and robotics. But I actually want to motivate an example that I think is a lot more practical and a bit more sensitive for why this is an important task. So on the left, we'll see 3 able-bodied people eating together, having a conversation. And this is a trial run for a robotic feeding arm. So this arm is going to acquire a bite of food and present it to this person who is playing the role of a user with upper mobility impairment that would prevent them from using the fork themselves. For this trial, this is actually an able-bodied person, which is an important note, but in general, that's the simulation we're trying to go for here. But I want you to watch the conversational dynamics versus what the robot does. All right, so I don't know if the audio is going through. Is it on
I
your
don't
end?
think.
Okay.
At least I didn't hear it.
Okay, that's fine, as long as you could see the people speaking. So the upshot
Right.
is they're having a conversation. We're doing standard sort of conversational turn taking. And what happens right there at the end is the person in blue asks a question. The person in pink is answering the question sort of in the middle of talking when the robot decides that it's time for her to take a bite and kind of shoves food in her face. So she's interrupted from talking to have to like break off her utterance and take the bite. And so another application for language and robotics generally that's worth thinking about, I think, is doing conversational understanding for the purpose of having better assistive robotics. So if you want to know when to actually present a bite to somebody, you need to understand whether they've just taken the conversational floor, if they're in the middle of talking, if they're likely to be talking soon, or if they've just offloaded the conversational floor to somebody else. And these are well-studied problems in natural language and dialogue. But now that we have sort of robot control that's sufficient to do these kinds of tasks, it makes sense to start merging these two things. So if you're thinking about fun things to do in a new space, I think there's very little work happening in that area, but it's a good application for language and robots. So I want to go back in time briefly, and I'll cut this video off a little bit early since we know that where the audio is not coming through. But this is, I think, roughly the state of the art in language-guided robotics circa 2018, which is when I was finishing my PhD. And what you'll see here is basically a good old-fashioned AI system of a bunch of different components sort of tied together to enable robot control with language. So I'll pause here and know what's going on. So I've given a command to the robot. It's done some initial processing of that command and identified that there's an adjective rattling that it doesn't know. So it has no idea what to do with that word. It's a brand new word in the vocabulary. This is an old school system. This is pre-BERT, large language models generally. So any word it knows is a word that I've hard coded to say, like, this is a word, this is what it means, here's how its syntactic functions work. Rattling is new. We can use a syntactic parser and say it looks like it's an adjective. It probably describes one of these objects, but now I've got to learn it sort of on the fly. All right, so I test some objects. That's a little bottle of pills that makes a loud sound when I pick it up and move it. All right, so we've sort of live gotten a positive and negative example. The robot asks for a couple more examples and that I go through. And then finally, it confirms the entire plan that I'm trying to get it to execute. So then we're off. What's happened here is we've used a statistical semantic parser to understand that lounge by the conference room refers to a particular location with respect to another location, right? We know where the conference room is. To refer to the lounge that's next to it, we have to identify this particular lounge is next to this particular conference room. Bob's office, we can then translate into a particular office number referring to a person who owns that office. And then finally, rattling container. We just learned the word rattling. We know the word container from some offline visual pre-training, which even in 2018, learning visual words was a little bit easier than anything else. And so we go to the lounge by the conference room, we see our candidate objects, and we grab the one that rattles, which in this case is this little pepper shaker. So then it drives over to Bob's office. Bob will come out of his office and grab the thing and shake it. If you had audio, you'd hear that the shaking is sort of audible when he grabs it and does the shaking. Just to confirm for everybody that it is in fact the rattling container. So if we flash forward to 2022, another paper also from my lab, but now 5 years have passed, and the state of language for robotics in terms of backbone models has changed quite a bit. So you remember a second ago, it had never heard the word rattling and had to learn it on the fly. We had to pre-explore all the objects. So when it saw those objects on the table, it identified them visually and then remembered basically feature representations that it had built for each of those objects. So it knew like what sound each one makes when it's shaken, what they feel like when you pick them up, what they look like visually, and could use that to say like, oh, this one must rattle without having to like actively rattle it right then and there. By contrast, flash forward to 2022, I can give a robot the language, sort the fruits in the plate and the bottle in the box with no prior familiarity of these objects, just running an image segmentation algorithm on the tabletop to identify these image segments, and then using a strategy called prog prompt to generate the actual API task actions that need to be taken. So rather than this bit in the previous example where I said move a rattling container from the lounge by the conference room to Bob's office, that was a particular task called relocation, where you drive to location A, pick up object B, drive to location C, drop off object B, right? And that's the only task you could do. In this example, all I have to do is say, hey, the robot can do pick and place, everything else you got to figure out on your own. And I can tell a large language model, sort the fruits in the plate and the bottle in the box. And with sufficient constraints, it'll generate a plan that says first grab the banana and put it in the plate, where banana and plate here are generated just from the image recognition model, like these labels for the thing. Grab the strawberry, put it in the plate. So I said fruits. I didn't even say strawberry banana. This is just coming for free, basically, from the common sense reasoning ability of the language model. Grab and put in bottle into the box. And then it leaves the drill alone, which is the correct action, right? Because the drill is not involved in the command. So in big contrast, 2018 to 2022, this system requires almost no pre-training, no looking at objects in advance for the robot. We can basically just take the language model and deploy it more or less zero shot on the robot system and have it come up with this pick and place plan that solves the task. So what changed here? Large language models can currently generate plan steps like this given language. If we tell them roughly like here are the actions the robot can take, or like make a plan for how you would sort fruits into a box or onto a plate and bottles into bags, it can do it. But they will generate actions that robots can't do with objects that don't exist if you don't constrain them. Because if you try to prompt a system for something like, oh, robot, I would like you to, help me in the kitchen by boiling some water. Large language model might generate a plan like, oh, the robot should go grab a stock pot, put it in the sink, fill the pot with water, and carry it over to the stove. And there are no commercial robots that can pick up a stock pot once it's full of water, right? That thing is like 20 pounds. Even two gripper robots probably can't do it. And most of them have single gripper like the one we just saw. So if it tried to pick up a pot full of water, it would just spill water all over itself and literally explode, right? So dangerous to use this kind of generation and directly execute it on a robot, especially without constraints. So what we introduced in this work called prog prompt that's cited there at the bottom, if you're interested in reading into it in more detail, is to specify what kinds of actions and objects are available to the system as some additional conditioning information. So this is a little bit of a middle ground between having to do everything by hand, like we did in 2018, and just letting the model do whatever it wants, which is what would happen if you don't introduce any constraints into the language model decoding. So we pull in a little bit of domain knowledge. What are the robot's actions? What is safe and what's not safe? What's available in the environment? So we encode the robot and world states directly into the conditioning info for the language generation. And what that looks like is if you've used a system like ChatGPT or any of these sort of API-based language models online, we create a prompt that's of this form that looks like a Python program. We'll have a library we make up called actions, and we say like from actions, import, and then all of the actions the robot can do. We say, hey, objects are just a list of strings, and this is all the objects that are available in the environment. Then we do some in-context learning where we give some examples of like, here's a task that you could do that are just like a sequence of actions taken on certain objects. And then the prompt itself for what to do next will just be a function signature. So in the example we gave a second ago of pick the fruits put the fruits in the plate and the bottle in the box, that would just be writing that out as a function signature here. And then when we feed that into a model like GPT-3, ChatGPT, Codex, it will generate a plan that looks like this little function call of actions that we should take. And then we can feed that into an interpreter that is API and agent specific. So if we want to run it on a particular robot, that interpreter will turn those calls into actual robot behaviors. Or in the cases where we need to check something about the world first, we can also query the language model about checking some state of the world. So here's an example of what this prompt actually looks like in a particular environment. So this is Virtual Home, which is a large-scale virtual simulation environment that has particular primitives environment. So it's instantiated in Unity. We basically create a symbolic representation of that Unity environment, and then we can specify things like our action list is going to be walking to a particular object, grabbing the object, switching objects on, opening them, closing them, standing up and sitting down. They're basically everything we could do in the simulation environment, we can provide to the prompt as examples of actions. Then we list out all the objects in the environment. That's basically taking a simulator state and just dumping it to a string list. We give some in-context examples, like here's how you would throw away a lime. First, you'd find a lime, you take a bunch of steps, you check and see if you're close to a garbage can. If you're not, you find it, you check if the garbage can is open. If it's not, you open it, and then finally you drop the lime in and close the garbage can. And then our prompt itself can be something like microwave salmon. So this is what the new task that we'd like to generalize to, given this information is constrained to the language model. So we feed that into something like GPT-3, and we get out this long list of actions that we should take. So walk to the kitchen, find the microwave. If the microwave is closed, or sorry, if you're not close to it yet, try to find it again. If it's closed, open it, down to microwaving the salmon and then putting the salmon on a plate. We actually keep going all the way to doing some extra tasks that are not specified here, right? Down to finding a plate, plating the salmon, putting it on the table eventually happens. So it'll generate more than we strictly need to do to finish the task, but it's neat to see this sort of common sense reasoning coming out. And you can ignore all these low level details. The important bits are we feed this to an interpreter that can do things like how do we check whether the microwave is closed or open. What we'll basically do is turn the environment state again into a string that describes the world, and then run the assertion examples as in context examples to GPT-3 again, and we can use GPT-3 to directly say, like, given this string description of the environment, does it seem like you're close to the microwave? Does it seem like the fridge is open, etc.? And then at the same time, we can actually execute the underlying actions like find and grab. So here's the simulation environment where we're doing things like open the microwave, grab the salmon, put the salmon in the microwave. And here's an example where we're actually executing the full task. So we walk to the salmon, find it, grab it, walk to the microwave, open it, put the salmon in, close the microwave, turn it on, turn it off, open it, grab it, close the microwave, and then it'll continue down to plating it and putting it on the table. And so that's the same underlying algorithm that we showed a second ago for controlling the physical robot. It's this general purpose sort of way of framing what are the constraints in the world, what are the actions the robot can take. And if we tell that to this large language model that already has some notion of common sense reasoning for solving tasks, we can say, solve the task under these constraints. You must use these actions, you must only use these objects, right? And then we're much less likely to have a robot that tries to do something like picking up a 20-pound pot full of water, spilling it all over itself and getting destroyed. So we can also plan on underspecified language tasks, which I think is cool. This is basically leveraging what language models are actually good at, which is doing well with the contextual examples that we give them. So if we tell the system to make dinner, for example, super vague, make dinner. If there's chicken in the fridge, it'll go heat up the chicken. If there's no chicken in the fridge, but if there's chicken and eggs in the fridge, it'll still cook the chicken. If there's only eggs, which are really more of a breakfast food, and we say make dinner, it will use the eggs. But it's neat to see that it's got this sort of like internalized preference ordering for what makes sense for make dinner. Like you have to make it, and if there's only eggs, you'll eat eggs for dinner. But if there's eggs and chicken, chicken is what it'll go for. And I found that kind of cool. It's basically giving us background knowledge to interpret the intent behind the instruction, even if that instruction doesn't tell us everything about what needs to be done. So this action and object information that we put into the prompt provides constraints for the constraint generation that we want the system to use when it's producing a plan. And highlighting what like enabled this to happen in the last 5 years is where I want to focus for the remainder of the talk. So this is really the emergence of what we're now calling large language models, right? Like the term LLM has become pretty ubiquitous within CS and especially sort of upended the natural language processing community. So the large language models together with like OpenAI's ChatGPT and the general notion of instruction-based fine-tuning have really kind of flipped the script and made a lot of the barrier to entry for using language for robotics applications much low enough that, you know, y'all are having a reading group where you invited me to talk about it because it's something that's actually within your grasp to do now, right? In a way that it most certainly was not in 2016 through 18 and certainly before that. So I want you to think about, if we take a step back from robots and just think about language interfaces and AI generally, can you think about language interfaces for AI agents that are in production now, places where you actually already see them? Any thoughts?
Benjamin is saying Google, Anthony Siri. It's a couple. We also have a
Oh, are we
question.
QA muted? Sorry, I didn't even check the thing to look have the chat open.
Here we go. So actually,
Yeah,
before we have a
Google, Siri. Yes, so those are good examples. Yeah, Siri, Google Assistant, Alexa, Google Home. These are sort of like either embodied in your phone or embodied on like a tabletop device that are definitely using language interfaces. They're probably using some large language models by now, even though they weren't initially, right? Largely, these things are still rule-based. I think like in the last year, they've probably started rolling out some like cautious optimism language interfaces for these things. But in the end, like they really don't want these assistants to do things or say things that are wildly inappropriate. And so they're pretty careful with guardrailing them and leaving them rule-based. And that's stuff like set a timer for 5 minutes, right? It's like something that you can map directly to an API call within the system for what it needs to do. Send a text message, place an order for more paper towels. And these things kind of look a lot like what I was talking about in 2018, where I said like move an object from point A to point B, right? It's that I've got like a particular thing that I know the system can do reliably, and I'm more or less filling the slots for the missing variables, like how much should the timer be set for, who do I send a text message to, what do I place an order for? And those are easier to write interfaces for, but they are places where we're starting to see large language models kind of creep in. So what makes them different now versus when we were first doing these role-based systems? To talk about that, we need to talk about what a language model is in the first place. And this requires going all the way to sort of fundamentals of natural language processing. So a language model at its core is an estimate of the probabilistic likelihood of a string. So to calculate that likelihood, it's most common to tokenize the string into components like words. So we can consider a string as a sequence of tokens. That'd be like word 1 through the word n at the end of the string. And the language model is just going to estimate the probability of that string, approximated as the joint probability of seeing those tokens in that sequence. So to sort of ground this out, again, little audience participation, consider the probability of these strings. The cat climbed the tree. Does this seem like a string that you're likely to see? Yes, no, maybe. Let's do a comparison. Is the cat climbed the tree or the dog climbed the tree going to have higher probability?
The cat climbed the tree.
Right. But why? We have some internal model of what it means for a string to be likely. So why is it more likely to see cat climbed the tree? It sounds like a stupid question, but it's important when we think about how we can impart that knowledge into a model.
Benjamin is saying the C is higher in character order.
I don't think that makes it more likely for us as people, right? This is more a question of like, why do you, a human being with like full scale knowledge of the English language, think that dog climbed the tree is less likely than cat climbed the tree?
Because our understanding of the world is more grounded in reality as opposed to, say, a language model understanding maybe more so the typical order of words, like how likely that is.
Yeah, so I think this is a fair assessment. Like for us, It's that these strings correspond to statements of fact. And when we imagine cat climbing tree, it's so typical that we're like, yeah, of course. And then when we imagine dog climbing tree, it's like there'd be a YouTube video of that, right? It's very funny. There probably are. So it's out of distribution, right? It's like it violates our understanding of the world in a way that causes surprisal. And surprisal is literally a measure of low probability, right? So when we think about how we would code this into a model, the typical way to do that is to have a language model read a corpus. Historically, corpora were like controlled data sources like Wall Street Journal articles or New York Times articles. But now that we have the ability to scrape the entire internet and big GPU training, it's become let's scrape the entire internet and just see what strings are likely on the internet itself. And so language models as of today, in the large language model sense, are more an estimate of what is the probability of seeing this string on the internet, which is a different estimation than what is the likelihood that a person thinks a string will happen, right? And I think that was the point that our audience participant just pointed, was like our knowledge is more grounded in the workings of the world. A language models is going to be more grounded in the token probabilities as seen on the internet. But they do share a lot of mutual information, these two estimations, like because humans, for the most part, are the ones who wrote the text on the internet for now. That's a whole separate problem. But we can extend this out. How likely does this string seem? It's got all the same words in it.
Pretty much zero.
Pretty much zero, right? Like even any particular combination of two of these words is really unlikely to see. And so this is the kind of thing that we're like, if we scrape the internet, we are going to get estimates that can at least tell us what's gibberish and what's not, right? And that's where this sort of like notion of coherence can start being applied to language generation. So we can use this kind of language model to generate text. This is the kind of thing that ChatGPT does in response to questions or commands from a person. So to do generation, I want to walk through the algorithm so we have like a statistical understanding of what's going on. We can factor the probability of a particular string into word sequences and then look at the probability of the next token. So you remember I said we're going to estimate the probability of a string as the joint probability of seeing each of the tokens in sequence. We can further factor that probability into the probability of the next token, Wn, given the string that's come so far, right? And so if we just write this out with Bayes' rule, that's probability of Wn given the words so far times the probability of the words so far, right? So the probability of observing the string that existed before plus this new token that may or may not happen. So we can estimate these probabilities directly by just reading the entire internet, right? This is effectively what these models have done even since 2012 or so, when statistical vector models first became popular. So we literally just look over some corpora of strings and see how often Wn follows W1 through N-1, right? Is it more likely that dog climbs house or dog climbs tree? So if we look at this estimate here, here's such an estimate for just Wn on the columns, or sorry, on the rows, and Wn-1 on the columns. So this is what's the likelihood of seeing the word the, given that I just saw the word the? Probably zero, right? Like it's really unlikely that you see the. It happens in like typos, right? But presumably this will get washed out. Probability of seeing the, given that you just saw students. So students, the, low. Learned the, maybe. About the, pretty likely. Today, the, pretty likely. In the, also pretty likely, right? So we can basically take these word counts and look over them, and then we get these particular spikes, like likely to see word vectors, especially in this talk where the students are learning about word vectors today in this lecture, right? Today in, also common to see as we like discuss a particular thing happening on a particular day. And so we get this sort of distribution of probabilities, and you can imagine generalizing this to having more than just one word in our history. Here we're just looking at what's called a bigram model, which is the probability of a word given only the word that just happened. So in general, these are called n-gram language models. This was historically the way that language modeling was done and that language model generation happened. So for a number of words that you want to think about, that's the size of your vocabulary. And then the number of words you want to look back is k. Then you need to estimate counts to get these probabilities for wk given all the k's that came before, right? So for 2 words, that's wk and wk-1, 1 and 0. For 5 words, it's 5 and then the 4 that came before. So the natural question that people have been asking since this kind of like in-gram language modeling first started in 2002, 3, is like, do we really need different word counts for words that are so similar, like forest and woods? If the previous words are things like the cat and the dog, don't we have a similar set of possible next words? Like the cat and the dog probably climb different objects, but the word climb is not unreasonable for both of them. The word like eats is not unreasonable for both of them. The word chase is really likely for both of them. And so it feels like we probably don't need this model of probability where every word gets its own column, where every word gets its own row, right? If you think about it that way, it's basically assuming total independence between words, that we need an entire independent sort of count vector for how frequently forest corresponds to different words or woods corresponds to different words. But in fact, there is mutual information between words, right? Synonyms exist, like paraphrases exist. And so you know the term word embedding undoubtedly by now. It was still a kind of a new concept when I was an undergrad, but I think in an AI reading group by now, hopefully this is a term you've at least heard. This is just a vector representation of a word that compresses word counts. You can literally think about it as a compression algorithm. And it comes from this early linguist concept called Firthian linguistics, where we have this famous quote that we've all sort of swallowed as NLP researchers. You shall know a word by the company it keeps. And this basically is the guiding principle of many of these learned word embeddings, that words that share a similar context, that is, that show up in similar kinds of text, should have embeddings that are close together and probably mean similar things. So this first became widespread with the introduction of the word-to-vec model. If you've taken an NLP course or studied sort of the history of NLP in any capacity, you've probably heard this term, word-to-vec. The basic idea of word-to-vec is you want to learn a neural language model. This was also one of the first neural nets that gained popularity in language, which was exciting. You have a neural net, takes in a word like happy. It has an embedding vector that it's actively learning. So these are the learnable parameters, the embedding of the language model. And it wants to predict, using a fully connected layer out to our entire vocabulary, the words that happened around happy. So this is going to be a multi-label prediction problem where it's predicting, in this case, the words like start of sentence, I'm today, and end of sentence, which is saying I'm happy today is what it's trying to predict out for a particular example. So if you do that over an entire corpus, taking a word and predicting the words that just showed up around it, then if you average all of those predictions, you're literally predicting the probability of the words that showed up around that word happy, which means you are compressing the n-gram count for the word, given how many words you want to look out to either the left or the right of the word and do this prediction. So you can build a model that directly estimates this big co-occurrence matrix, but instead of having the big co-occurrence matrix, you've only got the embedding vector, and the embedding vector has a compressed representation of what that co-occurrence matrix needs to look like. So instead of counting all the vocabulary words near a particular word, we're just learning this small vector that encodes those counts in a smaller space. So I can give a quick example of what this looks like, just to give you better intuition. So again, language models ultimately performing compression of this co-occurrence matrix. So what would you expect for this case? So it's a small sort of thought exercise. So we have this model, takes in a word, and it tries to predict for this word, what are the words that show up around this? What is their likelihood of being near this word? So if we give that embedding vector different sizes, what will be learned is different. So if we let that embedding vector be the size of the vocabulary, so basically our neural net is now one layer that's the size of the vocabulary. Say we've got only 100 words we care about. If we've got 100 words and we want to use a vocabulary size of 100, a vector size of 100 to predict 100 different activations of what words are likely, what will that embedding vector end up looking like if we train over the entire internet of our 100 words with respect to the co-occurrence matrix, I mean. I believe in you, and if you don't believe in yourself, ask a question, because then I can clarify if there's a misunderstanding of it.
Would it just be a probability distribution of how often you see these words on the internet?
Yes, it will literally just be the co-occurrence matrix as probability distribution, right? They won't learn anything. I mean, it won't have to compress anything, right? This is exactly the same problem as trying to estimate the actual probability distribution. So if we don't force it to do any compression, it won't compress. The vector will just directly be how frequently each word occurs near every other word. That doesn't get anything, right? It doesn't buy us any bonus over just doing the counting directly. But it's helpful as a thought exercise. So what happens? Sorry, these are called indicator features. Like it will literally just copy the output that it needs to have, right? Because it doesn't need to do any learn. It doesn't need to do any compression. What if we take away one dimension? What happens? We had a 100 words we care about. If we give it an embedding vector that's size 100, it can just learn indicator features that directly tell us what the probability is for every single word. It doesn't have to do any compression at all. If I take away one slot, what happens to my 100-word embedding vector? What does it represent now? Remember, I had asked earlier if we need separate counts for words like forest and woods. If we give the embedding vector size v, the whole vocabulary, then forest and woods get indicator features in the embedding vector that say, hey, the word is forest. I know that the word forest has this exact distribution versus here's the word woods. I know woods has this exact distribution. If we knock off one bit of that embedding vector, the most efficient thing the model can now learn is to take the two words in our vocabulary that are closest already and merge them. So for example, if we've got woods and forest in our vocabulary, maybe it just says, hey, it's either forest or woods. So my prediction is going to be the average of what I saw whenever the word was forest or woods. Does that make sense? And that's what happens. Every time we reduce the vocabulary size, we're basically telling the model, look, you've got to decide what words mean roughly the same thing or what words appear in roughly the same context. And you can have some like linear relationships between those things, but I'm only giving you, 300 dimensions to memorize 10,000 words. So you really gotta do some compression here and figure out how to put these words closer together in a meaningful space. So this is 2013. Each word has a single learned representation based on training on a huge chunk of the internet. This leads to a couple of weird corner cases. Since I mentioned we're treating words as white space tokenized strings, then we get situations like this where we've got a word, BASS, the lowest adult male singing voice, versus BASS, the common European freshwater perch, right? These show up as the same token in our training data. But if we look at three sentences, it's not clear for at least the last sentence which of these senses is even being used. And in the first two, these are very different. So there are a couple caveats on like why this particular learning style is not popular. And one of them is that it can't use contextual information. So this first sentence, we're talking about bass, right, on a guitar. Second sentence, we're talking about bass, the fish. Third sentence really could go either way. But if we have information from the sentence, we'll actually know which of these senses we're talking about, right? But in the word-to-vec representation that I just showed you, that string, BASS, is only going to have one embedding vector learned. So it will basically be the average of the contexts that we're seeing for both of these word senses. It'll merge them, right? And it'll merge them not because they mean the same thing, but because they look the same. They're graph phones, right? Like they're written the same way. Do you understand why this is a problem? It's hard without being able to see anybody.
Because when it comes to say words like bass, it's not truly learning the many different ways it can be used.
Exactly. It's assuming that the word is always used the same way. A core assumption of word-to-vec is that is this Firthian idea. You shall know a word by the context, by the context it keeps, company that it keeps. And if the word is defined as how we write it, as opposed to its underlying meaning, then we're going to merge words that are actually distinct. Like bass and base are two different words, but they are written exactly the same way. Consequently, word2vec merges them. So this is a difference between the Firthian linguistic notion that a word can be understood by its context versus the implementation by natural language processing and machine learning engineers that says a word is a string that looks like this, right? And so while we know these are two different words, the model does not, and it will merge them. So what changed is that in 2018, GPUs got big enough. What we really want, if we're processing sentences about bass and base, is to be able to look at the entire sentence when we process the word and understand it in context. So we want to combine these lexical embeddings, which are embeddings about the actual string, to produce a contextual embedding that is the string with respect to the entire sentence in which it appears. So this is, again, really made possible by the fact that GPUs got bigger, they got more efficient, and their cost went down. And the transformer architecture became the backbone of most natural language processing after 2018 because of the efficiency with which it runs on GPUs, especially for applications like this. So you might also know the term BERT, right? Bidirectional transformers for language understanding. So BERT hits the ground running in 2018, appends all of NLP, and it does so by just doing exactly what we just talked about for this bass-based example. Rather than creating a representation just for the word happy, we learn an embedding layer still. This is a learnable representation of the individual strings. So this is, again, a string just for the word happy, a string just for BASS. That'll be both bass and base. But instead of having that be the end game, we use a transformer architecture that just lets these initial embeddings talk to each other, basically, and say like, hey, I'm BASS, and another word in the sentence is guitar. And that tells us a lot about what the BAS string should actually be doing, right? It's that I'm a bass guitar. Versus if it's BASS and I'm the word fishing pole, then probably we're talking about bass, right? And what it means is at the end, we've got a representation for each word, like happy, that is not the string happy anymore. It's the string happy conditioned on the fact that it's in the sentence, I'm happy today, right? We actually have information about the surrounding context. So this is the difference also, just if you're looking at AI and NLP terminology, the difference between these is lexical embeddings, which are embeddings about the string itself, the token, versus contextual embeddings, which is the context in which the token appeared. Make sense? So this is a big change for NLP because it suddenly lets us reason about entire strings and put entire sentences into the same sort of embedding space rather than doing it on individual words, which rapidly changes our ability to do things like language-guided robotics. So if I want to tell a robot now, pick the fruits from the plate and put the bottle in a box, if I rephrase that as take the banana and the strawberry, put it on that white circle, then take the bottle and put it in that cardboard box, that's a totally different string. And in the old school AI systems, I'd have to know what all those words mean or use word2vec to try to approximate that maybe we're talking about the same thing. With something like this BERT architecture, I can put both those strings, run them through a BERT, take the representation of the start of sentence token, this one over here that says like, hey, I'm a sentence and my content is I'm happy today. And basically say, hey, here's a sentence that said, put the fruits on the plate and the bottle in the box. Here's a sentence that said that same thing, but much longer. But when I embed them with BERT, I see that these embeddings are super close together. Probably they refer to the same command. So suddenly we've got like open vocabulary, abilities for communicating language guidance to robot systems. This is what I mean when I say the barrier to entry suddenly went down so much, because we no longer have to hand engineer an entire NLP pipeline. You can say import Hugging Face, load BERT model, encode my sentence, right? And now you've got a vector you can do some reasoning on that gives you some sense of what the sentence might mean with respect to other sentences. And it's partially exciting because this same architecture, I mentioned this like transformer architecture became the backbone very quickly of most NLP. And one of the things it allows us to do is translation. So if I've got, this is just a pure NLP example, if I've got a sentence like two trees sway and I want to run that through a transformer sequence to sequence encoder, I encode it using a BERT style transformer over here. And then I have a transformer decoder that can say, what I want you to do is basically take this sentence and turn it into individual words in a target language like Arabic. And so I get all my target words become inputs for the next time step. And then I can keep running this same architecture to do predictions for the sentence in the target language. This is exciting because this is the same basic architecture that we can use for things like Robot Transformer, like Robot Transformer 1 and 2 that Google put out recently. Take in some conditioning information like a language command, and then one by one do a translation from that language to actions the robot should take. And it uses the same sort of underlying architecture as we see here for machine translation. All right, so one other note, since I mentioned there were actually two things that changed between 2018 and now. One was this large language models that can take in words and predict next words. They have the same underlying intuitions as Ngram models, but the thing that changed aside from GPUs scale is this notion of instruction fine-tuning. So most of the internet isn't chat data. It's not call and response, right? It's not like, there are not web pages for the most part that are somebody saying, hey, list all the state capitals, and then somebody responding with them, right? Like maybe Reddit looks a little bit like this, but most of the internet doesn't. Most of the internet is single author articles. So they don't look like chat. ChatGPT is weird. It's a call response. So if you were to give a language model something like, what are all of the state capitals, a pure language model, not something like ChatGPT, what it would be doing is trying to predict what words are likely to come next, given that the previous words will list all the state capitals. And if you think about documents on the internet that say, please list the state capitals, they're probably exams, right? Like a thing that if you play with one of these like T5 based prediction models will output, if you say, give me all the state capitals, it will next say something like, now list all the state flowers, now list, I don't know, the year of each state's incorporation into the US. Like it won't answer the question, it'll give you more questions that make sense in the context of asking that question, right? So to make these things chatty, sorry, this is an example of like how you would want a dialogue system to not just continue your text, but to make this thing chatty, remember that the function of a language model is just to predict the next word given the words that have happened so far. One thing that was happening before the release of ChatGPT, but that ChatGPT made very popular, was to think about this more in the way that we think about robotics. Think about language modeling as the estimation of a policy for what action to take given the context so far. So if you think about like policy learning and reinforcement learning for robotics, you can think about the actions as what word I'll say next, and the state as what's been said so far. And if we do that, we can actually do some policy gradient fine-tuning borrowed from reinforcement learning literature. And so this is the general notion of reinforcement learning with human feedback, or RLHF, which you've probably heard about or read about if you've looked at any of the ChatGPT sort of press releases and follow-up work. And the upshot there is that they have a big set of prompts, which is things that they would like the model to be better at responding to, like, can you list the state capitals? They give that to the initial language model. It's going to say outputs like, oh, also list the state flowers, or please also list the dates of incorporation. But maybe somewhere down the line, one of the language model outputs will be a set of capitals. Like maybe it's low probability, but if you sample from this thing, like a distribution for a while, at some point, one of these outputs is going to be capitals. It's not what the model thinks should happen. It's like very low probability, but it will come into the output. And what the ChatGPT insight was to have people rank those outputs. So annotators go in and say, when I asked for the capitals, I didn't want you to give me more exam questions. I wanted you to respond with the capitals. And so they'll say the capital response was actually the good one. And if we get a lot of that kind of data of people saying like, this was the response I actually wanted versus what you did, we can train a small neural model that just takes in the prompt, the response, and estimates what the person will say. Like, will the person like this or not? We use that as a reward, apply a reinforcement learning algorithm that just says, hey, try to respond a little bit more like the way that people want you to respond based on this reward model we trained on people's actual rankings of your responses. There's some regularization in there to make sure the language model doesn't totally fall apart and start saying strings that make no sense at all as it does this fine tuning. But the upshot is if we do this, we can get ChatGPT to respond with actual state capitals when we say what are state capitals instead of trying to continue our string. And we're doing that by sort of breaking the original language model objective. So it's no longer predict what string is mostly likely to come next. It's predict what string a person is likely to think should come next, given that they think that you're a chatbot. All right. So I'll recap the language stuff real quick. Language model can be used to generate words that correspond to distributions of training data. Learned representations let us share information between words used in similar contexts, like woods and forest. And then advances in GPUs have let us do that with longer contexts, improving generated text and taking into consideration the entirety of the sentence rather than just individual words. And finally, we can apply techniques from reinforcement learning to get a particular kind of behavior, like behaving like a chatbot. But you can get a lot of different kinds of behavior, and that's where some insights have started coming in for robot control. So there are things like language and vision alignment for robot control in the form of clipboard. So this is a very similar idea to Google's Say Can, where we had like the robot delivering the can from one counter to another. But here, these are examples of a robot in simulation doing tasks, completely open vocabulary, with a control policy that is just trying to get this command to be higher score with the visual environment. So the command is something like align the rope from the back right corner to the back left corner. We've got a model, like a language model or a language vision model, that gives a score that says, does this table look like the rope is aligned from the right corner to the back left corner? No, it doesn't. If the agent, like, as the agent pushes the string closer, the score gets higher, score gets higher, score gets higher. And then finally, once the string is all the way over here, the score is very high and the agent isn't able to make the score any higher. The score being, again, how well the text matches to the image. That text image matching is a similar technique where rather than embedding only the language, we want to embed the image and the language into a shared space so that we can calculate their similarity. So remember, all this bit about language modeling still applies. We can also embed images using like convolutional neural nets or vision transformers. I won't go into those in detail, but if we can learn a projection of the images, we can basically say, I have my BERT model, my GPT, whatever it is, to embed language, given this learned system that we just covered in the lecture. And we can basically add this extra constraint that says, I want to learn a projection that puts images and captions close together. So I want the language a rabbit sits in the palm of the hand close to the image of the rabbit actually sitting in the palm of the hand, while simultaneously pushing distractors apart. So I want the language, a white fox looking at the camera, to live as far away as it can from the rabbit without hurting our ability to be close to the caption. So this is the basic intuition behind another model you might have heard of, again, from OpenAI, called CLIP. The contrastive language image pre-training is literally just that idea, that we have a bunch of captions, a bunch of images, and we want to create a diagonal alignment that says, put the captions close to their images, put the captions of distractors far apart from those images. And that's sufficient to then deploy on actual language, on actual robots. We can do things like Google's early work in language and play embeds goal images, so here the robot controlling things, and language into the same latent space. So what image are you trying to accomplish? What is the language that describes accomplishing that? If we embed that into the joint space using the same kind of alignment with this big contextual language model and whatever our architecture is for encoding images, then we can, at test time, get a new command, look at the language at the joint embedding space, retrieve the goal image closest to that, and then we can do either, here's the goal image I want you to go for, or a language description that I want you to go for. And either way, the system can retrieve something it saw at training data and execute that. Recently, there was also the robot transformer and RT2. This is the same idea, but 3 years down the line, Google Robotics has gotten even bigger, gotten even more training data, and they can now do something close to machine translation, where they take in something like, put the strawberry into the correct bowl here, and then with every robot action, they get a new observation, which is new image, and they can do translation of what action should I do next, given that this is the last image that I saw. But it's the same underlying architecture and machine learning technique as sort of core machine learning, core natural language processing machine translation, using the same architecture, the transformer encoder decoder. And this can be applied for a number of different applications with and without the ability to do sort of dialogue and fine tuning. So I have some other things I can talk about, but I do want to leave a little bit of time also for additional questions. I know we paused a few times for my sort of open-ended questions to y'all, but I do want to give you a minute. If you have any questions for me, directions that you're excited about or want to learn more about, and I can try to take those as well in the last couple of minutes that we have.
I know there was a question earlier from Anushka. She's asking, by Pythonic prompts, does it mean Python language or prompts that mimic the way the Python reads or compiles instructions?
Yeah, so the Pythonic prompts is definitely just mimicking the Python language. And the core intuition there is that GPT-3 worked okay for this. What actually worked best was Codex. And Codex is trained on GitHub, right? So it's seen a lot of Python. Python also, unlike C, tends to use variable names that are very close to what they're actually talking about, right? This is just because Python is a younger language. It's always been interpreted. And so there's not as much of a tradition as you see in like C and Java of using variable names like A, B, C, D, I, J. Like Python tends to be like, I'm the iterator, right? And that variable name is very clear. So no, Python just reads a lot more like English in the first place. And Codex has read a lot of Python. So it was the interpreted language that seems to work best. There has been some cool, super recent work on trying to do this kind of like structure prediction through language models with DOM trees. If you're familiar, like currently in your CS courses, if you're doing anything in like web development, especially, HTML and DOM trees are something that all the language models read because they're actually reading like source material from web pages, not the rendered version, right? Which means they've read a lot of HTML. And HTML also, since it's written by people, tends to use variable names and like headers that are actually a little bit informative. So there's been some cool work in this space for like trying to do both robot control and tool control by predicting like what kind of looks like web page code, which is fun. Yeah, the upshot is just to try to use a language that you know the model has seen a lot of so that you have a basis of confidence that it's going to be able to do the prediction correctly and like, you know, close parentheses, close quotes, that kind of thing that historically language models were pretty bad at. But since they got very big and bigger GPUs and bigger data, they've gotten better at. But you still need to pick a language that they've seen a lot of.
Got it. We can take some more questions for a couple minutes. If you guys want to put them in the chat, or you can just unmute yourself and go for it. Wanted to a quick question on my own. I know you do a little bit of research on human and robot interaction as well. You touch a bit on what you're doing in that space and where you see that going in the future.
So the thing I'm actually most excited about right now for the space of human robot interaction is getting away from text. So even a long time ago, you know, even in 2018, it was common for people working in language and robotics, however few of us there were, to type the commands to the robot. It's just easier, right? So you saw in this video I showed of my like state-of-the-art robot 2018, I am talking to it and it is doing speech recognition. There's a microphone. It's got this little behavior where the arm like bobs up and down to let me know the microphone is on, but it was tedious. And if it gets something wrong, if it mistranscribes you or you don't speak clearly enough, it just does the wrong thing, right? Because it, even at that point, it was this closed vocabulary set of objects. So you couldn't hear the audio, but I'm speaking like very clear and monotonically so the ASR can understand me with as little accent as possible. But that's where we would actually want to interact with robots, right? So if you think about any robot system you would ever interact with, unless there's an entire app for it that has all the buttons for all the things you possibly want to do, in which case you're not doing language anyway, you probably want to talk to the damn thing. And so something I've actually gotten pretty excited about for the space of human robot interaction is just using the fact that it is a robot, that you are in the same environment with the robot to do better speech recognition. So I've got some recent work on embodied speech recognition where you just literally take into consideration the fact that you're in a kitchen when you're doing ASR, for example, and you can improve the speech recognition substantially because you know that a person is not telling you to, for example, put a ceramic vase in a microwave. They're telling you to put a ceramic plate in a microwave, and you can reason about that because they're holding a plate, or like there's a plate near you and you know you're in the kitchen. So like you can do some constraints on decoding speech by using the fact that you're a robot, by using like the context in which the person is talking to you. And we're extending some of those ideas right now to sign languages and gestures too. So for understanding American Sign Language, or for understanding sort of joint, like I'm speaking and I'm pointing or I'm looking, and that should tell us a lot about what I'm trying to communicate to the robot. And that's the space where I think core natural language processing researchers basically avoid this because they don't want to think about vision. It's hard. And if they do, they want to do clip, like just apply a model very quickly that gives me a score. Similarly, roboticists, for the most part, if they want to use language, they want to take import Hugging Face and just give it the text. And you can't do either of those things with speech, and you definitely can't do them with sign languages and gestures because those don't even have written forms. So that's the part I'm actually super excited about, and part of it is just because I know industry's not gonna get in there and do it first because they don't care enough, and it's really hard.
Right. That's super interesting. I think it's definitely an area where I want to do a little bit more research in, because it feels like, especially with what you're describing, it's not a space that many people in NLP are trying to get into, people or robotics are trying to get into. You want to take different elements from different places and put it into it, rather than creating something and really looking into something entirely new. Are there any other questions? Any other questions?
I I came late, so I was just wondering, will the slides be posted anywhere that I could potentially access?
I'm recording this, so we'll be posting it up after, so you'll be able to see the full thing.
Okay, awesome. Thank you.
For sure.
Actually,
thanks for doing that.
one more question for Professor
Go for it.
Thomason. I know your lab worked with the SURE program at USC last year. I was wondering if you anticipated working with that program again for the coming summer.
Yeah, we liked Sure. It was good. We had some good people come through it.
Okay, awesome. Thank you.
Perfect. All right, so any other questions? Final call. Awesome. And if there are no more questions, I want to thank Professor Thomason for doing this. It means a lot to us, and it was definitely a great experience for me, and I hope it was the same for everyone else. We'll, like I said, this is recorded, so we'll be posting it later. You guys will be able to see the full talk. If you guys, for people who came in late, people who missed it, you'll be able to see it later when we upload it. And yeah, we have piggybacking off NLP, we have our next meeting on Tuesday, where we get into some sentiment analysis, and we'll be having that 4 to 5 as well. So yeah, thank you all for coming out. Thank you, Professor Thomas. And yeah, let's wrap it up.